on the banners, right? So we should talk about it.
I'm like, I feel like I missed out.
Yeah, it's too bad. Yeah, last year was fun. Okay. So there are a couple more, which I don't have as much to say about. This is the last one I have more to say about. But okay, information-theoretic descriptions of measurement. So you guys might have heard of information theory. Anybody ever heard of like Shannon before? I think it's Claude Shannon. I want a cool name like Claude.
How do you spell it?
C-L-A-U-D-E.
Like Claudius?
Like Claudius. Ooh, that's another cool name.
So it's like Will for William, Claude for Claudius?
I don't know. Possibly. So, okay.
We'll talk trippy baby names later.
1.03, information-theoretic descriptions of measurement. So information theory studies information quantification, storage, and communication. Liberal use of it is made by metrology, which is the study and measurement, the study of measurement and applications. It's funny, I like miss whole words when I write.
Do you proofread?
Yeah, usually, but I have to admit that I've had to read a lot of articles to write this stuff very well, because I'm always like, okay, I got to get another perspective on this. So like I'm reading so much stuff for these notes that I don't always have time to go back and I'm doing it now. Is that okay?
You should talk to some of the adjuncts in the English department. Some of them have their own businesses, but they exclusively do proofreading for PhDs.
Oh, should.
You can write a book.
Yeah, I mean, this is, I don't know. I have mixed feelings. If I do write a book, I'm gonna make it be published in some place that's not, like, that doesn't take the ridiculous stance that these academic publishers have been taking with their stuff. There's gonna be digital stuff available for free, and the paper ones have to be reasonably priced. So.
Why are textbooks so very expensive?
Because you have to buy them.
Or just get them on Google for free.
Yeah. It's true. I know that too. I also get things from Google. Legally, certainly. I do only legal things. That's all I ever do, legal things. If there's ever a question, let that just be known now. I only do legal things. Okay. So, metrology. So it's the study of measurements and measurement applications. A measurement instrument can be considered an information machine that takes an input state of an object and yields an output reading. Okay? So it's kind of like there's information there to be transmitted. Information theory provides metrologists with a mathematical apparatus for computing the amount of information in a given information channel, typically in terms of probabilities. This same apparatus can be used for measurement, where we consider measurement to be the communication of information from the state of the measurement object to the measurement reading. The analogy between information transmission and measurement is incomplete, in that information encoded and transmitted is, in theory, known by the encoder, right? So in information theory, if you are going to send some information, you have to know that information before you transmit it to somebody else, right? So like in information theory, there is like a definite truth. Somebody knows it, and then they're going to encode this information and send it to you. Whereas in measurements, there is no person encoding it and sending it. So the analogy breaks down at a certain point, but it's still useful for what it is. So this is an active area of research. A related recent proposal is one by, I don't know how to pronounce it, Bas van Frazen? I just decided to go with the zzz on all of the S's. So this posits two levels. A physical level at which the instrument yields a reading of the state of an object, and an abstract level in which measurement reduces the region in which a mathematical representation of the physical state exists in a state space. That was a mouthful. But state space is, okay. This is something that you guys haven't, not all of you know about. Some of you know a lot about it, though. High five, back row. All right. So the rest of you will learn a lot about state space, and you'll love it. It'll be one of your favorite things ever. For now, think of it as being, say you were going to describe the dynamics of a point mass, like you did in your dynamics classes. You had equations to write down for it. Like, for instance, you could write down Newton's law, F equals ma, second law, and like the x and the y. Your state space would be the. Have you guys taken linear algebra yet? No.
I have.
A couple of you have. If you took the variables that you describe it with, like the position and the velocity, and you created a, you could think of it as like, if you haven't taken linear algebra, you think of it as like different axes, different dimensions of a space. If they generated a space, then as the object moves around in space, has different velocities, it would essentially be equivalent to moving around in this state space, right? It would have a certain position, a certain velocity, and that would be represented by a point in the space.
So like basically like imagining the universe as like a giant grid of everything, where you can track the movement or properties of said object.
Yeah.
The grid that is.
Yeah, you could think of it that way. Essentially, you're describing a limited state. You're saying, okay, this is a point mass, and it has, say, in one dimension, has a position and a velocity in one dimension. That actually, if you know those two quantities, you know everything about it. You can describe all of its motion. That is a state space model for a point mass in one dimension. But you could do, many dimensional state space. So. Oh, it's really fun. Oh, we're gonna have a lot of fun with that. Back row is like so on board with state space, and what we could think of measurement as being is that before we measure something, the object, the state of the object could be anywhere in all of its state space, right? But what we're doing when we're measuring is we're shrinking down the places it could be. We're saying, okay. Well, we know that its position and its velocity are, somewhere in this region here with a certain probability. That would be how an information theorist would think of measurement. Well, that's how this guy, Bas van Frazen, would think about measurement, which I think is a pretty cool way to think about it. That's why I told you guys that this was his theory.
So, was it the same guy? I can't remember who said that anytime you effectively measure something, you change it.
There's so much to that. So at the quantum level, there's the reaching into memory.
Not enough RAM in that one?
No. Oh my gosh. Uncertainty principle. There it is.
Showing this uncertainty.
Wait a minute.
Yeah.
Uncertainty,
Yeah.
like that.
So you can't measure both the position and the velocity of a particle exactly. The more you know about the position, the less you can know about the velocity. So there's also, you could say, even at the level that we understand measurement typically, whenever, and this is something that I haven't noticed a lot of discussion of in the textbook or in any of the stuff that I was reading, but that is whenever you measure something, you affect it, right? If you're going to interact with it in the world, you have to affect it in some way. So for instance, you can't measure a voltage without affecting what the value was. Also in quantum mechanics, when you measure something, do we want to go there? You collapse its wave function. You guys know what a wave function is? Okay, let me tell you. So in quantum mechanics, you can say that a particle doesn't have a definite position until it's measured. Okay? It has a probability distribution where it could be. Once you measure it, it takes on a definite position. But before you measure it, it doesn't have a definite position. So, once again, your measurement affected the outcome. Interestingly, at the quantum level, there's all this stuff called quantum weirdness, which is like you can prove. You can.
called that? Is it
It's really, there are papers called like quantum weirdness and blah blah blah. Like it's quantum weirdness. It's stuff that you wouldn't think is the case based on our macroscopic interaction with the world.
It's almost like Schrodinger's cat.
Yeah, that's Schrodinger's cat. That's the whole idea. Is that you don't know? It's not that you don't know that the cat is dead, but the cat's not dead until you've seen it dead.
Once you've seen it dead, it is dead forever.
Yeah, but I will say that at the macroscopic level, there is I think most physicists think that observation doesn't have to be just some like a sentient being observing something. So like nature can observe itself. So like a cat can die without somebody, like a person opening the box. But at the quantum level, if you want a particle to be in a certain place or not, you have to interact with the particle. Weird stuff. I don't know. I can't even begin to say that I understand all about quantum mechanics. But quantum weirdness is fun because you can prove it. You can do measurements where you can prove that your measurement affected the outcome of the measurement. So weird. It's almost like the particle knew where you were going to look. Like, look up the what is it called? There's a really I don't know.
Rosenberg.
It's like Rosenberg something experiment, but it's like the first one that was like really just totally weird, freaky quantum mechanics experiment that was done.
Do light particles do what people expect them to do?
Yes.
Is that where they split and it creates two?
I don't know. We got to move on. We just do. We can't do quantum mechanics all day. It would be fun.